Okay, everybody, we are ready to start for our last two presentations for today. And I'd like to introduce our next speaker. That's Shrikant Acharya. I hope I pronounced that correctly after many years of practice. He's also going to address the topic of TSN and also some Shaper-related discussion that we're going to have, and the presentation is titled Use of TSN for Real Data in a Zonal Architecture. Okay. And everybody get back to your seats, please. I should have said that first, I think.
Hello, everyone. While you're getting seated, I'll talk on a more humorous topic here. And that is, I was not supposed to present here, but my colleague was, but then he was sent to USA, so I had to come from USA to come here. So when I tried to arrange my trip here, I was all concerned about what pre-trip, will I ever even reach here? Can I present in the conference? Will I be held back at the port? And when I come here, I suddenly start worrying about how to get back. And so now I have to figure out how to get PCR tests. All of a sudden, the conference is the last thing on my mind, when it should be the first thing on my mind. So I'm glad that that's behind me. So to get started, my name is Shrikant Acharya. I am the CTO of Excelfore, and we have been a player in the automotive for about over 20 years, or at least personally have had that much of experience on different topics. So today's topic, of course, is a practical one, which is to bring these wheel sinks. The challenge with all these technologies have been, like, if you look at these issue of tire pressure sensors and wheel sinks, these have traditionally been separate ECUs that are linked through wires directly from the sensor points into an ECU which computes. But zonal architecture could ease some of the routing and also the computational architecture going forward. I know a lot of OEMs are touching on the zonal controller, while majority of their aspects are still weighed with the domain architecture. So with that said, let me get started. So this is a joint development with Aptiv. We have been developing zonal controller architecture from a software aggregation standpoint for backends that are 10 gigabits up to 16 gigabits. And it's always a challenge as to how you bring something that is more practical, that is usable today. And so this one was something that was that Aptiv undertook as something that OEMs need. And so this is a result of that collaboration. So with that, let me get started. So use of TSN for wheel sensor data in a zonal architecture is our topic. So one of the challenges today is with the look at the amount of bandwidth, first of all, the technologies have evolved. You have connected car on one end, and you have autonomous driving on one end. So these are challenging the scope of how networks have been designed. So it has three challenges which come up very clearly, and that is the complexity. So you will have to address the complexity because the number of uses are large. The code bases in each of them, if you aggregate them, becomes a substantial body of work. And so how do you validate it? So that's complexity. The other one is, of course, labor cost, which all of us know now. The other one is the automated driving complex control structure itself. So these are all the challenges. But there is a benefit in all these new technologies that is coming along, is that the amount of bandwidth that has dramatically increased also brings in, you can bring in the quality of service into your architecture, which is a good thing. So what does zonal architecture objectives are? I mean, the objectives are simplify, basically reduce the number of functions into smaller groups, unite all the applications into little bits that are controllable. And then, of course, OEM gets the power to control all of the user experience. Now, what's the design philosophy? The design philosophy is to abstract software from hardware. And that's, to a large extent, some of the service-oriented conversation we have had early in the morning reflects that abstraction, because what you're doing is taking abstraction and then you're separating the IOs from the compute elements, and then you're trying to bring them all to a central server, and so it's a serverization of the process. So in many ways, you are breaking down how the control elements all get aggregated. So signal communications are separated from the service. So in a multi-zonal architecture, you see that you have all these ECUs that are, some can be replaced, but some are going to stay. And this could be your door controller or your wiper seats. And then you have these audios, elements, and real sync is one of them. So you see that there is a distinct level where you are controlling these elements, and that becomes your signal interface. So you bring them into a zone. So the zone then either can become a service interface or still stay a signal interface. And now you can move that, aggregate through a network into your compute elements. So the compute elements can then connect to the server in the backend. So the central compute can become your service gateway. You can pass that service down to a zonal gateway, but that's the decision that you make for a specific design. Now, take the case of a wheel speed sensor. So this is a real practical application today. So what happens in the wheel sensor today? So the wheel itself has what I call ticks. These are equally spaced, what I call spokes, or you can say timing signals that will come out of the wheel sync because it's just spoked, and then a pickup just picks them up and transmits it to a central ECU, which could be an ABS or a electronic stability control. So these are, sometimes you can use 28, some are using 96. So for the practical discussions for our experiment and test, we are going to choose a 28 spoke kind of a wheel sense system. So in this wheel sense, each wheel connects the pickup into the ABS ESP. So you can see that if the ABS ESP is sitting in the back of the car, you have to bring all the connections individually from each of these pickups into the back. So that presents a challenge for harness. So this, I mean, you can see field speeds, steering angles, there's a whole bunch of them. So what are the constructs of this system? The construct of the system is, it's a critical signal because a brake and stability is involved. And the signals have to reach the decision point within 1 millisecond. So those are the guiding things for us. And of course, they are critical. So you take the wheel sense, which is in the analog sense in the previous, what I call slide, to how do you convert into a more digital place for our calculations. So wheel speed sensors provide a digital signal. And so they're giving you this timer ticks. So essentially, the faster the wheel rotates, the ticks will come faster. But the distance is constant, so you know how the wheel is moving. It's a requirement that when you try to digitize, you're building a system that can transmit the signals in a timely shape. So we are mandating an Ethernet-based system, and of course, most systems are getting there. And so you limit the packet size are quite limited. So what you encode in is a 7822 packet, which has a 32-bit timestamp. You have the sensor number, so that way you identify it, you identify the pulse, and you have a information unit that you transmit. Now, the way you look at it is that the wheel rim can be 16, 15, 8, 19, and so that remains how the speed works. So that also sets the frequency at which the signals come from each of these wheels. So if you take a 28 pulse per wheel and you actually run it at 200 kilometers per hour and you take a default, say, 16 or 17-inch wheel, you'll get something between 610 hertz to 810 hertz kind of a signal. So we decided that we would take a 1 kilohertz signal that actually is a good gauge for the speed. So now we laid the analog system out. So now I'm laying out the digital map of that same structure. So in this case, we have a zone in the front in which the two wheel sync pulses are brought in. And then you have individual zones in the rear that are bringing these signals into the zone. So, and then the zones then communicate to a central compute controller where the decision can get made. And from the zonal controller, it can go to the ABS ECU. All this mapping has to be done within 1 millisecond. So now you can see that by connecting the pickup of the wheel sense into the nearest zone, I have basically mapped it to the nearest point. So direct impact on how much less harnessing I'm going to use. So in this case, the two signals come to the front and the individual zones in the back. So we have basically 3 zones in this setup. And so we are using a 1 gigabit Ethernet network, and the red lines are a pulse inputs. That's how the wheel sync comes in. Now, how do you create a system that reflects what we just had shown? So we created 3 zones. So the 3 zones will have a microcontroller interface that brings in the signal from the pickup, converts into a TSN packet. That needs a way to get injected into the network. So you need a front-end switch that translates that. So accumulation of all zones then gets to a TSN switch. Now remember, this is for all kinds of traffic. So we have a site traffic injector as well in this process. So it's trying to model a network inside the vehicle. So in the previous slide, we saw that you had 4 inputs. So you had 4 asynchronous talkers coming in, right? And so you had 2 steps, as you can see, if you go back. So if you look at it, you have the 4 signals coming in. So those are the talker inputs. Then there are 2 hops before you end up in the decision control ASIC. Now, how do I set up my system? So I need to validate how these things are happening on a scope. And also for analysis, I want to take them into a, say, PC where I'm just collecting this data for analysis. So the other challenge you have is that last year it was very hard to procure systems for anything. And so we had to innovate as to how to get what we wanted and still be able to simulate and get the proper results. So in this case, we got a one real controller, which is the S32K that has the input in it for a real wheel sync in, and then use simulated pulses that reflect the wheel sync from a PC. So then all they're brought up into this at 100 megabits into the TSN switch, including the injector. You had a cascade that get you the 2 hops, came into this controller in the end, and then you had 2 things there. So you got a timestamp update and a signal feedback to when that signal was received. So you have a T0 timestamp that enters the gate and a T1 timestamp that comes at their reception. And then you have 2 signal pulses that are telling you on the scope as to the injection point and the exit point. So to summarize what our test system for this thing is, the main requirement is we have to conform to this 1 millisecond time frame end to end. And so the zone controller S32K connected to the 1105 creates the 1722 packets. And now to set up the experiment, you have to have, without the what I call prioritization, where all signals get the same priority, which is having no shaper, what happens when you give them priority, and what happens when you give them priority and you inject. So those are our test experiment points. So the payload for the injector is, as I said, a short unit for each signal that comes out of the wheel sense. So your load generator is just constantly pumping 100 megabits into the switch, and a central controller at the end, which is an S32G, but it can be anything else. But since all our development is what the tier 1 is propagating, we use the setup that they have prescribed. So each wheel pulse and the generated pulse from the 33 is then visualized, as I said, in a logic analyzer, and also captured in a logger. So here, pictorially, I represent what the setup was. So you have the S30DG, which is our main aggregator where the control loop or compute loop is set up. You have the PC that generates the synthetic wheel pulse. You have the real controller that's generating the actual wheel pulse. And then you have the setup as we just outlined. So now we have the setup. We have now turned on our wheel sense generation at the input, and we have the experiment to go forward. So first is basically your standard setup, which is no traffic whatsoever. What is our, what I call standard, what I call latency. So in this case, we have taken about 170,000 kind of samples. And what you see is the latency is about 57 microseconds. And the latency gap is between 54 and 61. So the standard deviation is quite low. And you can see for a major part how the signals are concentrated because they get full priority and they cross the channel in a prescribed time. So that's not a problem there. The latency in the max case is only 85 microseconds. So remember, our end latency is always 1 millisecond against which we are mapping. So 85 microseconds clears it by a great margin. Now, if you start bursting traffic on the side traffic channel, then, and so now we turn on the credit-based shaper to see how that is making the performance any different. And what you're seeing is that the performance is unchanged despite fully loading the channel at the input. If you use the credit-based shaper, you're first of all, the sample signal is short. And so it is, even if you are having the payload go into the credit-based shaper, you're getting the gaps, and then the signal is passing through. And what you're seeing is the total latency is still 85 microseconds. So in this case, you can see that all the real signal and the synthetic signals are all within certain range for you. Now, if I look at how the signals are verified on the scope, so you have the analysis on one end and what you're observing in the scope. And you can see it actually maps quite well. The latency gaps are within range. So if you look at north side traffic, which is your copacetic, is between 55 to 60 or 53 to 60. And then when you're loaded with side traffic, it actually varies from the low of 42 to high of 60. Now, when I don't, so now if I give where I do not give priority to the time sync signal, what you're seeing is now the signal is getting transmitted in a random fashion. So it can show up at any point in the cycle. So the greater the channel side traffic, the broader is the distribution of the what I call the wheel sync. So you can see that all of a sudden, I cannot predict as to where this will insert itself. And with the same sample size, you can see your average latency has suddenly shot up to 117 microseconds, and with a max latency of almost 345. Now, if you look at it, the 345 microseconds still gives you a third of the margin for what is needed. So 1/3 is the 345. You still need 1 millisecond. So even if you actually don't use any site, you need full site traffic, but if you have enough bandwidth in a channel, you still you don't need the traffic shaping. And so every one of these signal types, whether it's synthetic or otherwise, is showing you the broad distribution as to how the behavior is for the critical signals coming in. So you'll see the delay has expanded. So how do I analyze these test results? So one without any shaper and no traffic, one with shaper with all traffic, and with full traffic and no shaper involved. So in all of these cases, in credit-based shaper, the critical traffic is completely not impacted. So that's a good thing. And so P2 traffic will not be pushed from the queue so long as the class is guaranteed sufficient bandwidth. So then if you have sufficient bandwidth for the critical signals, it's always get through. And without the credit-based shaper, if the total network bandwidth exceeds the traffic that you're inputting, you'll still meet the critical timing. But the key thing to understand is that the timing is not deterministic for you. So that means it'll come at any point in the link. So that's your challenge. And so if your site traffic expands to a higher number, or your basically your throughput is 1 gigabit becomes 100 megabits, for example, as your end, you'll start to see some challenges there if you don't use the credit-based shaper. So in the final conclusions, what we are trying to do is, can a wheel sync, which has traditionally been used as an analog interface into the ECUs, can this become digital? Can it be routed through a zonal controller? Are the setups right for such a characterization, so this becomes a easy way to put together? The answer is unequivocally yes, because that clearly shows that you have the credit-based shaper available, and it does the job. And we are using a 1 kilohertz signal. Now, what we have seen is that you can go up to 4 kilohertz too. So you can, if you want to run at, if the number of pulses per wheel round or wheel cycle is going to be high, it'll increase the frequency. So in that case, it can go up to 4 kilohertz. What are the net nets that I can say? So your 1 gigabit, I guess, is equally good. But what we do if you reduce the trunk from, say, 1 gigabit end-to-end to, say, 100 megabits, which is available in some network topology, a credit-based shaper still will be sufficient for you. But if you boost it to 4 kilohertz signal, we believe 1 gigahertz trunk would be equally good. But if you have 100 megabits end-to-end network, we may have an issue to deal with. And the up integration. So one of the things that the zonal controller will do is you can absorb some of these ECUs in your compute elements. And so your up integration with other ECUs can be a real advantage for you, because you're not making individual connections from the sensor to your end ECUs. So that's a big advantage for you when you try to redraw your map using a zonal controller. And with this, what we have proven is that OEMs can use and redirect from a traditional wiring to what I call a zonal wiring. Thank you.
Okay, thank you very much, Shrikant. I have a question to you. Of course, I've seen all presentations in their first review before they were shown. And I've also seen this one, of course. And then that presentation, you talked about the time-aware shaper, and now you've changed it to the credit-based shaper. And I'd like to know why, where this came from.
And I actually went back. It was a good thing that you pointed out.
Mm-hmm.
And the challenge with time-aware shaper was, of course, I wrongly.
You might need to go to the microphone.
The challenge with time-aware shaper is here the input signals are basically asynchronous. Mm-hmm. So time-aware shaper could not do the job. And so I had to go back and revisit the assumptions. Mm-hmm. And so I corrected myself in the paper.
Okay.
So that to me, I highly appreciated the review, because it forced me to go and do a complete revision, redoing the, what I call tests, to make sure everything was right. So thank you for that.
Okay, well, I'm glad it helped. And happy about the results. So we have one online question, it looks like. Oops, that's my badge down there.
And I'm having to use the laptop. For some reason, my phone isn't cooperating. So I got a question from Christoph Golob. When you're talking about traffic shaping, you mean sending side traffic shaping at the talker, allowing traffic to merge together more smoothly, right? That's the, I'm just reading it literally there.
So I think this morning's talks about what CBS does is this gives you gaps. And so if you have prioritized these signals, what happens is it allows it to go through, and it actually allows, so even if you take maximum, what I call size of the Ethernet packet on your side traffic, you're still able to get through. So even if it's taking a long time, because you're no longer allowing a side traffic to take over, which is what I think Max talked about, right? So if the side traffic just expands to a lot, then it will lose the priority signal. But we tried the full max length packet and still were able to get the results through. Does that answer his question?
I don't know.
I don't know.
We hope it does.
Let's hope.
Yes,
Any other question from anybody in the audience? Okay, Max is getting ready for his next presentation, not for asking a question. Then thank you again
Right,
for your presentation.